wait for 5 minutes before we start this session. Okay, so today we will be discussing problems of assignment sheet for week 7, which involves problems related to Riemann integration. So let's start with first question. Let f be a real valued function defined on real variables, be continuous, and further using this f we define a new function capital Fx which is equal to integration from 0 to x squared plus x plus 1 f by dy for every x in R. Then we have the following options. First one, f dash x is equal to 2x plus 1 f x squared plus x plus 1 for every x in R. F dash x is equal to f x squared plus x plus 1 for every x in R. F dash x may not exist, and D says f dash x is equal to 0 for every x in R. So basically, we need to find the derivative of some integral function. So basically, derivative of a function which is defined by some integration of some functions. For that, a very useful result is the Leibniz integral rule. So I'll just recall that. Recall the Leibniz integral rule. So it talks about the derivative of integrals of some integrable functions. So if f is continuous or at least integrable, then the derivative d by dx of this integral, which is defined from ax to bx. So basically, our limits are again of some functions of x, and we are integrating a function which depends on two variables, x and y. Basically, we have another variable y, dy, and in this case, this derivative is equal to fx y replaced by bx times d by dx of bx. So basically, we replace y by bx and multiply it with the derivative of the upper limit minus fx ax, this time y replaced by the lower limit and multiplied by its derivative, plus integral of from a to ax to bx, integral of the partial derivative of f with respect to x by dy. So in this case, we are integrating some function which is completely depending on a y only. So in that case, this will eventually be 0. So let's see how our uh, derivative will be. This implies d by dx of, in this case, ax is 0. Bx is the function x squared plus x plus 1. Fy, it is depending only on y, will be equal to fx. So since we do not have x, just y, and y will be replaced by the upper limit function, which is x squared plus x plus 1 times the derivative of the upper limit. So it's just 2x plus 2, sorry, plus 1 minus f of lower limit times the derivative of the lower limit, 0, plus integral 0 to x squared plus x plus 1, and the integral of the partial derivative of f with respect to x, which is 0 here. So this is equal to just 2x plus 1 times, and this is for every x wherever the function is well defined. So this will be f x squared plus x plus 1. Now, since the inside function here, this is our capital F, this gives us d by dx of fx is equal to 2x plus 1 times fx square plus x plus 1 for every x in R. And this is our first option. Therefore, first option is correct. I hope this is clear how we use the Leibniz rule. I would like you to just recall this Leibniz rule. This is a very important rule. One should always remember it. And yeah, this was just a very good application of Leibniz integral rule. So if you have any doubt in this question, please let me know. Okay, so if there is no doubt, we'll move to the next question, which is something related to the function of bounded variation. So, question number 2. We say a function f defined from close AB to R has bounded variation if there exists some positive real number, k positive, such that this summation I from 1 to n minus 1 mod f xi plus 1 minus fxi, this is less than equal to k for any this partition, we call it partition, or I'll just write a equals to x naught less than x1 less than x2 and so on up till xn. So basically we have n plus 1 elements in this closed interval a to b, such that the smallest one is the lower limit or just a, the smallest one is the a and the largest one is b, and then we have some n minus 1 terms in between a and b. So no matter what a and what these points we take in between a and b, this type of inequality should hold, and this k should be independent of the choice of these points. Then we say that the function has bounded variation. So state whether true or false that every Riemann integrable function Riemann integrable function has bounded variation. For that, it will be a very good exercise for you. You can try it yourself. That every function of bounded variation is actually Riemann integrable. You can consider it as an exercise and try if would prove that every function of bounded variation is actually Riemann integrable. All you need to use is the definition of Riemann integrability and this function of bounded variation. So try it yourself. And the converse of this is actually not true. So we can remember it as every function of bounded variation is Riemann integrable, not conversely. That means the function, if a function is Riemann integrable, it need not have bounded variation. Now, since I'm saying that the converse does not hold, I should be able to give you some example. So I'll explain it clearly with an example. So this does not hold conversely. We will see how. So a very good example that contradicts this converse of this statement is the following function. We define f from close interval 0, 1 to r as fx is equal to x sine 1 by x for x belonging to open 0 to close 1 and 0 when x is equal to 0. We all know that this function is always continuous, and in fact at x equals to 0, the limit is actually equal to 0. Now, since limit x tending to 0, x sine 1 by x, you can easily prove this using standard methods that this is equal to 0, which is equal to f of 0. Therefore, f is continuous, at x equal to 0, and hence, because otherwise it's just x sine 1 by x, we do not have any issue. So it is eventually continuous, and hence it is continuous in the whole domain close interval 0 to 1. And we know that since every continuous function defined on a bounded interval is defined on closed and bounded interval is Riemann integrable, therefore f is Riemann integrable. Since every continuous function defined on a closed, and this I think you must have done in your theory class. This is a very good result. Every continuous function defined on closed and bounded. In fact, continuous functions, we do not, I don't think we need the boundary also. Continuous functions are always integrable. Yeah, provided the domain is bounded. Oh, yeah. Defined on closed and bounded domain are Riemann integrable. So therefore, this function is Riemann integrable, but we will see that this is not a function of bounded variation. For that, we should be able to get some partition such that corresponding to that partition, this sum is actually going to infinity. We'll see how. So, consider the partition. Consider the partition P, collection of all those xk's, where xk is equal to 1 upon k plus 1 by 2 I. And this will be um, for yeah, obviously this is always less than equal to 1. And with k belonging to n. Okay. So corresponding to this partition, let us see how does our xk plus 1, sorry, instead I should write f of xk plus 1 minus f of xk. How does it look like? So this is equal to, since we are not, our partition, we'll just remove the terms. So I can write it as union 0, union, yeah, then only we can call it a partition over closed interval 0 to 1. So except for point 0 and 1, let's see what happens at the points in between. So basically we have 0, 1 and some points in between. So suppose this is some xk and here this is xk plus 1. So we see what happens here. This is equal to, by definition, 1 upon, so this is equal to xk plus 1 sine 1 upon xk plus 1 minus xk sine 1 upon xk. And this is equal to 1 upon k plus 1 plus 1 by 2 pi sine k plus 1 plus 1 by 2 pi minus 1 upon k plus 1 by 2 pi sine k plus 1 by 2 pi. So this is equal to 1 upon k plus 3 by 2 pi sine k plus 3 by 2 pi minus 1 upon k plus 1 by 2 pi sine k. So yeah, I can write it as k pi plus 3 pi by 2. So this is k pi plus 3 pi by 2 and this is k pi plus pi by 2. Now when k is odd, so k pi plus 3 pi by 2. So when k is odd, that means we have 1 pi, 3 pi, 5 pi. So 5 pi plus 3 pi by 2 will eventually, so if we look at like this, so this will be somewhere here, and this plus pi by 3 plus pi by 2, 2 pi by 2, 3 pi by 2. So eventually will lead here. So in that case, this sine of k pi plus 3 pi by 2 will always be equal to 1, and sine of k pi plus pi by 2, we will be just here. So this will be equal to minus 1. And when k is even, in that case, sine k pi plus 3 pi by 2. So in this case, we will be starting from here, plus 3 pi by 2, pi by 2, 2 pi by 2, 3 pi by 2. So this is equal to minus 1. And sine k pi plus pi by 2 is equal to 1 in this case. So overall, we can say that this implies sine k pi plus 3 pi by 2 is equal to minus 1 to the power k plus 1. Because whenever k is odd, sine k pi plus 3 pi by 2 is equal to 1. So when k is odd, so say suppose 1 or 3, so we get minus 1 to the power 1 plus 1, 2 or 4. So that gives us 1. Similarly, we can see the even case, and in this way, sorry, sine k pi plus pi by 2, this can be written as minus 1 to the power k. So this, from here we get, this is equal to mod 1 upon k plus 3 by 2 pi, and sine k plus 3 pi by 2 is just minus 1 to the power k plus 1 minus minus 1 to the power k upon k plus 1 by 2 pi. So this is taking minus 1 to the power k outside, and since we have modulus, so everything turns out to be positive, because this can be now written as, now we can take minus 1 to the power k plus 1 outside, and since we have modulus, it does not affect. So we are just left with 1 upon k plus 3 by 2 pi plus 1 upon k plus 1 by 2 pi, which is eventually equal to 4 times 2k plus 2 upon pi, or this is just taking LCM and simplifying everything. So this will be 2k plus 1. Now I say, and now this is greater than 4 by pi 2k by 3. Why? Because 2k plus 2 is less than, so this is greater than 2k plus 1. So 1 upon 2k plus 2 is less than 1 upon 2k plus 1. Okay, wait just a second. I think yeah, yeah. Therefore, 1 upon 2k plus 1 is actually greater than 1 upon 2k plus 2, and multiplying it by 4, 2k plus 2 upon 2k plus 3, this will be greater than 4, 2k plus 2, 2k plus 3, and 2k plus 2. So this is just 4 pi as well, 4 by pi 2k plus 3. Therefore, we get this inequality. So therefore, what we got, we started with this mod fxk plus 1 minus fxk. Now this implies mod fxk plus 1 minus fxk. This is greater than 4 by pi 2k plus 3. So taking summation k from, now since we have taken k for all natural numbers, so k is starting from 1 to infinity. So this is k from 1 to infinity, mod fxk plus 1 minus fxk. This will be greater than 4 by pi summation k from 1 to infinity 1 upon 2k plus 3. And we know that this series diverges. Now, since summation 1 upon 2k plus 3 is a divergent series, you must have, because this is similar to summation 1 by n, you must have seen that this 1 by n goes to infinity. Summation 1 by n goes to infinity. This series is divergent. So this is some sub, we can say that the sequence of partial sums corresponding to this series will be actually some subsequence of a sequence of partial sums corresponding to this series. So eventually this turns out to be divergent. And since the smaller one is divergent, that means the larger one is going to infinity. That means summation k from 1 to infinity mod fxk plus 1 minus fxk. is goes to infinity. Therefore, we got a partition corresponding to which this we call this the variation. This is called the variation of the function corresponding to partition is actually going to infinity, so it cannot be bounded. Therefore, f cannot have bounded variation, and hence the given statement is false. I would like you to go through the solution once again and see how we have proved that the variation of this function cannot be bounded. So the main idea is to take this type of specific partition. In fact, you could start with the taking partition this to be Pn, and for taking this k to be in between 1 to up till n, and then further taking n tending to infinity. So then you get a sequence of partitions corresponding to which the variation is going to infinity. So variation cannot be bounded. Yeah, that would have been a better way. So I'll wait for 5 minutes. Please go through this again. If you have any doubt, please ask. I'll get in more detail. Suppose f has bounded variation. That means there exists some k positive such that the variation, I will write that variation of f corresponding to any partition Pn will be less than equal to k for every n and n, where this VFPN is nothing but summation k from 1 to n mod fxk plus 1 minus fxk. That means by first 4 by pi, yeah, this will also be after n. Summation k from 1 to n, 1 upon 2k plus 3 will be less than summation k from 1 to n mod fxk plus 1 minus fx, and this is equal to the variation of function f corresponding to the partition Pn. This is less than equal to k. This tells us 4 by, or instead of that, summation k from 1 to n, 1 upon 2k plus 3. This is strictly less than k pi by 4 for every n in n. Now, since we have dependence on n on the left hand side and the right hand side is independent, taking limit, we get limit n tending to infinity, summation k from 1 to n, 1 upon 2k plus 3. This is less than equal to k pi by 4. But since limit n tending to infinity, summation k from 1 to n, 1 upon 2k plus 3. This is infinity because we this I think I hope you must have done this result in while studying the series concept, that this type of series is actually divergent and it goes to infinity. We get contradiction. We get a contradiction, and hence the function f does not have bounded variation because we started with assuming that it has bounded variation. Get a contradiction, and hence f does not have bounded variation. Therefore, the given statement is false. Yeah, I think this proof should be fine. Yeah, now please go through this again. If there is some issue, please let me know. Okay, so if there is no doubt, we can move to next question. Next question is a straightforward application of again that Newton, the Leibniz rule, Leibniz integral rule. I'll just explain. State whether true or false. Let f from a b to r be Riemann integrable, and let s and t be some real numbers such that this s squared plus s plus 1 and t cube plus t square plus 2, both these real numbers belongs to this closed interval a to b. Further, define fs and ft, two functions from closed interval ab to r, as fsx is just integral from s squared plus s plus 1 to x of the function fu du, and this ft at point x, this is equal to t cube plus t square plus 2 up till x f u du. Then they're saying that this fs minus ft is actually a constant. Now, since I'm saying that this is an application of Leibniz rule, you must have got some idea that eventually we need to differentiate somewhere. So now, since they are saying that this is equal to constant, so what can we say about the derivative of this function? If we know that a function is constant, can we say anything about its derivative? So basically, a function is constant. A function defined on closed and bounded interval is constant if and only if its derivative is 0. So now, if the function was to be constant, its derivative must have been 0. So that means we can say that fs minus ft, this is equal to c if and only if d by dx of fs minus ft is equal to 0. Now let's look at the derivative of this function fs minus ft. So if I define a function h, just for the sake of simplicity, fs minus ft, then d by dx of h at point x, this is equal to d by dx of fs at x minus ft at x. So by definition, this is d by dx of integral s square plus s plus 1. Now this s square plus s plus 1 is just a real number. This is not a variable. So we need not worry about this s while differentiating with respect to x. So that is actually just a constant fu du minus d by dx of the integral d cube plus d square plus 2 x fu du. So in both the cases, we can see that this inside function is independent of x. This lower limit is also independent of x. So by Leibniz integral rule, this is just equal to f u replaced by the upper limit, this is just x, and multiplied by the derivative of the upper limit. So the upper limit is just function x, the derivative of x is 1, minus f u replaced by the lower limit s square plus s plus 1 times the derivative of the lower limit with respect to x. Now this is s square plus s plus 1, which is independent of x, therefore the derivative is 0, plus integral s square plus s plus 1 x, and we need to integrate the partial derivative of f with respect to the partial derivative of this fu with respect to x. Now since fu is also independent of x, so this is 0, minus, again in this case it will be fx times 1 minus f t cube plus t square plus 2 times 0 plus 0. So this is just fx minus fx, which is 0. That means the derivative of the function h is 0 for every x in closed interval a to b, which implies that hx is equal to some constant for every x in a to b. And what was hx? Hx was fsx minus fs1, sorry, fts, ftx. This is equal to some constant for every x in a to b. Therefore, the given statement was true. So yeah, this question was just a very direct application of Leibniz rule. Please go through the solution again, and if you have any doubt, you can ask. Okay, so if there is no doubt, we can move to next question. Hmm, again, state whether true or false. Let f be a function defined from closed interval ab to R, and let pk be a sequence of partitions, a sequence of partitions of closed interval ab, and the sequence is such that this limit k tending to infinity upkf minus lpk plus 10f is equal to 0. Then they're saying that in this case f is Riemann integrable. So firstly, one should know what do we mean by these UPF and LPF. So for a partition P, which contains the elements of the interval A to B, such that the first term x naught is A, then we have x1, x2, so on up till xn, the last term is equal to B. This UPF is defined to be equal to summation k from 1 to n mk times xk minus xk minus 1, where mk is the maximum of the values of fx for x belonging to the subinterval xk minus 1 to xk. So if we look at it graphically, if suppose this is a function defined on interval a to b, and then we have a partition. Suppose we start with just 3 4 elements. So this is our x naught, x1, x2, x3, and this b is equal to xn. So what are we doing? We are actually we consider firstly this subinterval. Okay. So we consider the subinterval and then look for the maximum value in this function. So in this subinterval. So in this subinterval, we can notice that this is kind of increasing. So maximum value is something here. So we are multiplying this maximum value with this x1 minus x naught. So that gives us the area of the rectangle that has length equal to this mk. This is the length and this is the breadth. So basically we are looking at the area of this interval. Similarly, here the maximum is somewhere here. So we take area of this interval, this rectangle, and in this we are looking for area something like this, and eventually we are just adding up all areas of all these strips. So one can notice that the finer the partition will be, the sum will eventually lead us to the area under the curve of this function. So that's the idea of integrability. So we eventually make our partitions to be more finer, so that eventually will lead to the integral. So yeah, and hence this UF, we call that UF is just the infimum of all these sums. So basically, you can see that the sum of all these strips is greater than the area under the curve. So as we make the partition to be more finer, the area tends to decrease. So eventually we want our area to be decrease towards the area under the curve. So we take this UF to be infimum of all UPF, where P is any partition of P is a partition of AB. Similarly, we define this um, LPF. LPF is nothing but the summation k from 1 to n, small m k, xk minus 1, where the small m k is the minimum value of the function f in the subinterval xk minus 1 to xk. So in this case, suppose let's look at the first interval. So in this case, the infimum is something somewhat here. So we are taking sum of this rectangle. Then we are taking the area of this rectangle. The In this case, the infimum is somewhat here. So we are taking area of this rectangle and area of this rectangle. Then we add up all these rectangles. So in this case, the sum is lesser than the area under the curve. And hence we tend, and more finer the partition is, the area increases. So in that case, we say this LF is equal to supremum LPF, where P is a partition of AB. This UF is called the upper sum. We call it the upper sum or the upper integral. And this LF is called the lower sum or the lower integral. And we say that a function is integrable if this LF is actually equal to UF. So basically, once we make the partitions to be finer, the upper sums are decreasing towards the curve and the lower sums are increasing towards the curve, and eventually we get the area under the curve. So a function, we say f is Riemann integrable, Riemann integrable if this LF is equal to UF. So we'll see in our case that if we have a sequence of partitions such that this kind of identity holds, in that case the function turns out to be this integrable, Riemann integrable. Let's see solution. Now since we are given that limit k tending to infinity UPKF minus LPK plus 10F, this limit is equal to 0. Now, by the definition of limit, for any epsilon positive, we can find a natural number n such that this modulus of UPKF minus LPK plus 10F, this is less than epsilon for all k greater than equal to n. Now, since UF was actually the infimum of UPF for any partition P, so this is always less than equal to UPKF, and this happens for all k greater than equal to n as well. It actually happens for every k, but we are specifically interested in k greater than equal to n. Also, since LF, this is supremum of all LPF, where P is a partition. So this is greater than equal to LPK plus 10F for all k greater than equal to n. Again, it happens for all partitions, so it happens for LPK plus 10F. It happens for all partitions, therefore it happens for pk plus 10 also for all k greater than equal to n. And this gives us that minus LF is less than equal to minus LPK plus 10F for every k greater than equal to n. Now adding up, we get UF minus LF is less than equal to UPKF minus LPK plus 10F. And we know that this is less than equal to the modulus UPKF minus LPK plus 10F. And this is strictly less than epsilon for all k greater than equal to n. Now, since epsilon positive is arbitrary, we can take epsilon to be tending to 0 because this implies UF minus LF. The left-hand side is independent of epsilon, but the right-hand side has epsilon. So taking epsilon tending to 0, we get, in fact, it is independent of K as well. So we do not need it. Taking epsilon tending to 0, we get UF minus LF is equal to 0 because is always positive, UF minus LF. So we get it to be less than equal to 0, which implies that UF is equal to LF because by definition, you can easily see that UF is always greater than equal to LF. So this gives us UF less than equal to LF. We already have UF greater than equal to LF. So eventually we get UF is equal to LF, and hence by the definition F is Riemann integrable, and the given statement is I hope this is clear. Please go through the solution again and the definition of this Riemann integrability. I hope this is clear how we are using the partitions and this condition on the partitions to get that this specific function will be Riemann integrable. I'll wait for 5 minutes. Please go through the solution once again. And if you have any doubt, you can ask. Yeah, if you have any doubt, please let me know.
And can you scroll the screen below?
Okay, so if there is no doubt, we can move to next question, question number 5. State whether true or false. Let f be a function from closed interval ab to r being Riemann integrable. Then for any c positive and t in r, the function f c t defined from closed ab to r as fct at any point x. This is equal to mod sin c times f at a plus b minus x plus 2 to the power minus t for every x in AB. Then they're saying that this function is Riemann integrable. Is Riemann integrable. So all we need to use is the fact that f is Riemann integrable, and then some epsilon delta definition corresponding to the Riemann integrability. And using that, we will see that this FCT will actually eventually be Riemann integrable. Let's see how. So as discussed earlier, a function is Riemann integrable if UF is equal to LF. Accordingly, we can say that F is Riemann integrable if for any epsilon positive there exists a partition P which depends on epsilon such that this U FP epsilon minus NFP epsilon is less than epsilon. So this comes directly by the definition of UF and LF, basically because we are trying to minimize this difference UFP minus LFP. Since we are minimizing this distance difference UFP and LFP, For any epsilon positive, we should be able to get. So since f is Riemann integrable, if and only if UF minus LF is equal to 0. That means this UFP minus LFP goes to 0 in some sense. That means for any epsilon positive, I should be able to get some partition such that this UFP minus LFP is very small. The idea is to make this UFP minus LFP to be as small as possible. So we should always be able to get this partition P epsilon. Um, that means now I will use this partition P epsilon to show that similar kind of condition is satisfying for the function fct, and hence it is also it is also Riemann integrable. So let's see how we can use this. So, mm, okay, consider the partition. Okay, so we have not explicitly written P epsilon, no? Suppose P epsilon is equal to, suppose this P epsilon is equal to x naught a x1, x2, so on up till xn minus 1, xn equals to b. Now using these xi's, we will make another partition of closed interval b. As follows. Consider this yk to be equal to a plus b minus x n minus k for every k 0, 1, 2 up till n. That means this y naught will be a plus b minus x n, which is a plus b minus b because xn is equal to b. So this is a. A1 will be a plus b minus x n minus 1, which is strictly greater than a plus b minus xn. Why? Because xn minus 1 is strictly less than xn. So yeah, that gives us minus xn minus 1 is greater than minus xn. And then just adding a plus b. So moving on in this way, yn will be a plus b minus x naught. And since x naught is equal to a, so yeah, a will get cancelled out. This is just b. So P bar, which is equal to y naught a, y1, y2, so on up till yn minus 1, yn equals to b, is a partition of closed interval AB. And we will show that corresponding to this partition, this UPFCT minus LPFCT will be less than epsilon. So now for x belonging to yk minus 1 to yk, and where k is equal to 0, 1, 2 up or up till, and it can take any value. When x belongs to this subinterval, we get yk minus 1 less than equal to x less than equal to yk. That means minus, yeah, by definition, this will be a plus b minus x n minus n minus k plus 1 is less than equal to x less than equal to a plus b minus xn minus k. And this gives us that minus a minus b plus xn minus k plus 1 is greater than equal to minus x greater than equal to minus a minus b plus xn minus k. So why are we actually doing it? Because in the definition of this FCT, we need to find the value of f at a plus b minus x. So we need to see what happens to f of a plus b minus x when x belongs to these subintervals. So now that means xn minus k plus 1 is greater than equal to a plus b minus x, and this is greater than equal to xn minus k. This implies a plus b minus x. This belongs to the closed interval xn minus k to xn plus 1 minus k, and where k can be anything from 0 up till n. So we need to find u p. So this is p bar. Nu p bar for FCT minus LP bar for FCT. So by definition, this is equal to summation k from 1 to n, capital MK. And since this is for FCT, I'll write CT in the superscript, times xk minus xk minus 1 minus summation k from 1 to n, small mk ct xk minus xk. So this we can combine it. So this is k from 1 to n, mkct minus mkct times xk minus xk minus 1, where this capital mkct, this is equal to maximum of fct x, x belongs to xk minus 1 to xk. Sorry, we are working on p bar na, so this all this should be y. Our partition is p bar. So this is yk plus 1 minus, sorry, yk minus yk minus 1, yk minus yk minus 1, yk minus yk minus 1, and this is from yk minus 1 to yk. And similarly, small mk ct is minimum of the function fct in the subinterval yk minus 1 to yk. Now, for x belonging to yk minus 1 to yk, we know that a plus b minus x belongs to, yeah, let me mark it as equation 1. This belongs to this closed interval xn minus k to xn plus 1 minus k. So that means f a plus b minus x is greater than equal to small f, and this is n plus 1 minus k till capital M n plus 1 minus k, where m n plus 1 minus k is minimum of the function f when x belongs to, or instead I should write just mk to make it easier to understand, x cubed to x cubed. So, and capital MK is maximum of the function fx and x lies in the interval xk to xk plus 1. So that means, yeah, further in the definition of fct, so that means mod sin c n m n plus 1 minus k plus 2 to the power minus t, this is less than equal to mod sin c f a plus b minus x, and this happens for every x in yk minus 1 to yk plus 2 to the power minus t, this is less than equal to capital M n plus 1 minus k plus 2 to the power minus t, and this is happening for every x in yk minus 1 to yk. Hmm. That means capital M C T K, this is equal to, yeah, this is multiplied by mod sin C as well. This is less than equal to mod sin C times mod sin C times M n plus 1 minus k plus 2 to the power minus t, and small m k c t, this is equal to mod sin C m n plus 1 minus k plus 2 to the power minus t. Now using this above, okay, I'll mark this equation as number 2. Using this in equation 2, so yeah, we get up bar fct minus lp bar fct. This is equal to summation k from 1 to n. Instead I should write it below. This is equal to summation k from 1 to n mod sin c capital M n plus 1 minus k plus 2 to the power minus t minus mod sin c m n plus 1 minus k plus 2 to the power minus t times we had yk minus 1. I'll replace this yk minus 1 also. So this is equal to summation k from 1 to n. Yeah, this will get cancelled out, and we can take this mod sin c to be outside the sum. This is equal to mod sin c summation k from 1 to n m n plus 1 minus k minus small n n plus 1 minus k, and this yk is a plus b minus x n minus k minus a minus b plus x n plus 1 minus k. And this is mod sine c summation. Now if I replace, take j to be equal to, take j to be equal to n plus 1 minus k. So we get summation j from when k is equal to 1, this is n, and when k equals to n, this is 1. So yeah, this will be mj minus small mj times, and here all this will get cancelled out, b. So we are just left with xn plus 1. So yeah, that's j, xj minus xj minus 1. So since this is just finite sum, I can change the ordering. So I can write this to be equal to mod sine c times summation j from 1 to n, mj minus small mj, xj minus xj minus 1. Now this is equal to UPF minus LPF. Mod sine c UPF, if you can see back, that I don't think, UFP epsilon. UF P epsilon minus LF P epsilon. And we know that we were given that F is Riemann integrable and hence this was less than epsilon. If I take that epsilon to be epsilon by, yeah, if I take this to be, that's in my hand, I can take this to be epsilon by mod sine c, just so that I get this to be upon mod sine c. So this will be equal to epsilon. Therefore, UFCT for P bar minus LFCT, P bar is less than epsilon. And since epsilon positive is arbitrary, we get this UFCT is equal to LFCT, and hence the function f is Riemann integrable. And we actually write it like this: Riemann integrable on closed interval a to b. Therefore, the given statement is true. Please go through this solution once again. It might be a bit calculative and in detail. If you have any doubt at any step, please let me know. I can wait for 5 minutes. We can discuss if you have any doubt at any point. So all we have used is the fact that f is Riemann integrable and hence we have a partition such that this condition holds. And using this partition, we constructed another partition P bar for the function this FCT, so that eventually we get U P bar FCT minus LP bar FCT B to be less than epsilon. Okay, so if there is no doubt, we can move forward. Next, question number 6. Again, state whether true or false. Let F from close AB to CD be Riemann integrable and G from CD to R is continuous, then the composition GOF from AB to R is Riemann integral. So yes, this will be true, and in order to prove this, we will use the fact that this function g is continuous on closed and bounded domain. So eventually it will be uniformly continuous and its range will be a closed and bounded interval as well. And using that uniform continuity of this function g, we will eventually get the Riemann integrability of the composition. Uh, since g is continuous on a compact domain, sorry, this is singular, CD, this implies G is uniformly continuous and bounded as well. Now let epsilon prime uh, positive be arbitrary. Then for epsilon equals to epsilon prime upon a plus b plus 2m a minus b plus 2m. We'll see how we get that. Uh, Positive. We can always find, uh, yeah, instead I should write, this implies, basically we'll be using the definition of uniform continuity. That means for any epsilon positive, we can find a delta positive such that mod gy1 minus gy2, this will be less than epsilon whenever mod y1 minus y2 is less than delta. So I'll mark this as first. And by boundedness, there exists some m positive such that mod gx will be less than equal to m for every x in closed interval c to d. Let's mark this as equation 2. Now, since f is Riemann integrable, f is Riemann integrable, this implies for above delta positive, for above delta positive, we can find a partition P such that obviously this P depends on delta. U F P minus LFP, this is less than delta. So we mark this as option 3. Okay. Now suppose this partition is equal to, now suppose this partition is P, x naught equals to C, x1. Sorry, since now this P is integrable on close AB, na? So this should be equal to A, A, x2, so on up till xn minus 1, xn equals to B. Now we will show that this composition is also integrable. So basically using this partition, we'll somehow show that U GOF P minus L GOF P is less than epsilon. So firstly, let's see this UFP minus LFP. Now UFP minus LFP, this is equal to summation MI Mi minus small mi times xi minus xi minus 1. Now I'll subdivide this sum because this is just a finite sum I from 1 to n. I take all those i's such that this mi, capital Mi minus small mi modulus is less than delta on one side, and the rest of the i's in the other one. In this case, mi minus mi is greater than or equal to delta mi minus mi xi minus xi minus 1. I hope you understand that we can always do this. Okay, so we call such sets, such the collection of all such points, all such i's to be good set, and this one to be bad set. We'll see how. So basically, if capital Mi minus small mi is less than delta, then this mi star, where mi star is maximum for GOF, mi star minus mi star will be, so I should explain that. Huh? Okay. I'll do that. Now, this UGOF P minus LGOF P, this is equal to summation mi star minus small mi star times xi minus xi minus 1. You can notice that I have taken the same partition. So I can again subdivide this sum into two sums, because mi star are actually the maximum and minimum corresponding to the composition. So I can write this as summation mod mi minus mi less than delta. See here, this is mi star, and I am dividing the sum exactly in the similar way as we had done earlier. So that's why here we had capital M, just mi, not mi star. Times xi minus xi minus 1. Basically the sum over good set, good points and the bad points. So now Mhm. For the good points where mi minus mi is less than delta, whenever y1 y2 belongs to the corresponding interval xi minus 1 to xi, we will get mod fxi minus f, sorry, this will be, yeah, still we have modulus, no? So no problem. This will be, obviously the difference between 2 points will be lesser than equal to the difference between the maximum and the minimum. So this will be less than equal to mod m capital Mi minus small mi, which is strictly less than delta. Now since fxi minus 1 minus fxi is less than delta, by uniform continuity of g, this will give us that g fxi minus 1 minus fxi, g of fxi, this will be less than epsilon by uniform continuity of G. And that gives us that mod GOF, yeah, instead, oh, this is y1 minus y2, no? This is just y1 and y2. y1, y2, y1, y2. So this gives us GOF y1 minus GOF y2 is less than epsilon for every y1 and y2 belonging to this interval xi minus 1 to xi. That means our capital Mi star minus small mi star will be less than equal to epsilon. And hence the summation mod Mi minus Mi less than delta, the set of points, set of good points, Mi star minus Mi star xi minus xi minus 1, this will be less than equal to epsilon times summation xi minus xi minus 1, and this will be obviously less than equal to epsilon times summation I from 1 to n xi minus 1, which is equal to epsilon times b minus a. So basically the sum over the good points is equal to epsilon times b minus a. So next we will see what happens on the bad points. And for capital Mi minus small mi greater than equal to delta, we have delta times summation mi minus mi. So anyways, this modulus has no effect. Delta xi minus xi minus 1. This is greater than equal to summation mod mi minus mi greater than equal to delta mi minus mi xi minus 1. And sorry, this is less than equal to delta is less than this, no? Less than equal to. And this is less than equal to UPF minus LPF, FP, and which this is less than equal to delta. Now, if I take this to be, because this delta was in my hand, I started with some arbitrary delta uh, in the definition of integrability of f. If I had taken this to be delta square, so yeah, because this delta was arbitrary, so this I can get here delta square. So eventually what I'll get summation capital Mi minus small mi greater than equal to delta xi minus xi minus 1 is strictly less than delta. Now this implies, so we actually had to sum over this mi minus mi greater than equal to delta mi star minus mi star, xi minus xi minus 1. This will be actually less than equal to 2m, because mi star is maximum of the function f for g. So which is obviously less than equal to the maximum of the function f. And this eventually this will be less than equal to 2 times m, because capital mi star is less than. So this is less than equal to mi star plus mi star, because everything is positive, and this is less than equal to m plus m 2m times summation mod mi minus mi greater than equal to delta mod xi minus xi minus 1. This will be less than 2m delta. So what's happening? Basically, this tells us that the set of bad points is actually very small. It has weight very small, because this delta can be taken as small as we want. So if I mark these equations, this one has star 1, this one has star 2, this one has star 3. So using star 2 and star 3 in star 1, we get u g o f p minus l g o f p is less than epsilon b minus a plus 2m delta. So if this delta is taken to be smaller than epsilon, this turns out to be less than b minus a plus 2m times epsilon for delta less than epsilon. And we had taken this epsilon to be equal to epsilon prime times b minus a. I told you in the starting itself. Oh, this is plus, this is minus. So this will be equal to epsilon prime. Hence, for any epsilon prime positive, we were able to get a partition such that UGOFP minus LGOFP is less than epsilon prime. That means this GOF is Riemann integrable on closed interval a to b. I hope this is clear. Let's move to next question. Last question, question number 7. We need to again state whether true or false. If we are given that a function f a b to r is Riemann integrable, I'll write in short. And we define gx to be equal to fx whenever fx is non-zero, and 0 whenever fx is equal to 0. Then they're saying that g is Riemann integrable as well. So what do you think, whether this is true or false? If we have a Riemann integrable function f and we define g such that, oh, this is equal to 1 by f whenever f is non-zero and equal to 0 whenever f is non-zero. So will that g be Riemann integrable? So basically that's not true. For that we can give a contradicting example. Define f from close interval 0, 1 to r, f of x to be equal to x. We know that f of x equals to x is a continuous function defined on closed and bounded interval, therefore it will be Riemann integrable. This f is Riemann integrable on 0 to 1. And if we define g exactly in the similar way, then we have g from closed interval 0, 1 to r, and gx will be equal to 1 by x when x is non-zero and equal to 0 whenever x is 0. So we all know that this function is not integrable at all. It blows up at 0. So since g is not Riemann integrable on closed interval 0 to 1, therefore We get a contradicting example, and hence the given statement is false. I hope the above solution and this is fine with everyone. If you have any doubt, you can ask. No doubts. Okay, then we can end this session today. End this today's session, and we'll meet next Saturday. Okay, then. Thank you.